Hi everyone, this is Yukabuka and welcome to my home on YouTube. In this video and a few of the subsequent videos, we will look at how character devices are implemented within the Linux kernel. In order to do this, we will look at the source code of an open source dummy character device and look at the functions that are exposed by the Linux kernel which allow for character devices to be created. The device driver that we will be looking at is the one you can see at this link. It's github.com/starpos and the name of the repository is SCULL. And within it, we will be looking at the simple.c driver file. Within this directory, we can see that there are a couple of other scripts for the inserting and removal of device drivers. As we will be doing most of our testing, if at all, on a QEMU ARM or ARM64 system, this doesn't really apply. So let's just dive into the source code. The source for this driver was written with the intent of demonstrating how device drivers can implement memory mapping. As a result, we will look into that as well. However, we will first start off by looking at how a character device can be implemented and what functions are exported by the kernel. Okay, let's get into it. If we look at the source, we can see that a couple of things jump out at us. There are a few include files, and after that there is a simple major value, and there is something called a module param of simple major. A module param indicates that this is a value that defaults to 0 unless it has a value passed in from user space. So it is possible to specify this parameter value when inserting the module into the kernel. There is the module author and the module license, and that's it. We see that simple open is not really implemented, it just returns 0, and closing is just the same, it just returns 0. There are a few functions for named VMA open and VMA close. We will eventually look into that. However, a quick glance, we can see that all it's doing is just printing out information about the VMA struct that has been passed into the function. We can see that the VM start, VM_page off values have been printed out. Something interesting is that it says a virtual as VM_start and a physical as VM_page off. And well, the virtual part makes sense because VMA arrow VM_start would point to the virtual address of the mapping, the start virtual address of the mapping. However, VM_page off left shift by page shift. I'm not quite sure how that ends up being converted to the physical address. But we will try to figure that out eventually. VMA close is simple as well. It's just a message being printed out. And here we can see a static struct of type struct VM operations struct. And that has two elements, open and close, and these functions are set to those attributes it's set to those function pointers. So what we can do is, let's take a quick look and see what kinds of fields are present inside VM operations struct. If we go into the struct, we see there is a comment. There are virtual memory management functions, opening of an area, closing and unmapping it, needed to keep files on disk up to date, etc. Pointers to the functions called when a no page or a write protected page exception occurs. Fair enough. So for each of these events, there is a function pointer, and those function pointers are called. There is one for open, close, split. I'm not sure what split is. There is remap, fault, huge fault, map pages, page make write, and the comment says notification that a previously read-only page is about to become writable. If an error is returned, it will cause a SIG-bus. I see. So effectively, if the driver implements some form of memory sharing using mmap, and the privileges on those set of pages are set to be readable, and if there is a write attempt, then this is the function that will be called. So there is an opportunity for the handler, if it chooses to do so, to instead change the protections on that to writable as well, and then return a no error. So that's effectively what it means. There is another function pointer here called pfn mkwrite, which says that it is the same as page mkwrite when using VM pfn map and VM mixed map. I'm not sure what that means. We can perhaps, maybe we will run into that in the future as well, but as of now I don't know what that is. We can take a quick look though, because I am mildly curious. So what this means is it's a page range managed without a struct page, just a pure PFN. That's strange. I did not know this was possible. So every frame of physical memory in the system is managed in the Linux kernel by a corresponding struct page structure. What this suggests is that there are page ranges without a corresponding struct page, and instead they just have a pure PFN. So in order for such mappings, perhaps this flag is used. I'm not sure why there would be page ranges without a struct page, but yeah. There's also a mixed map. Let's have a quick look at what that is, because I just want to know. VM mix map says it can contain a struct page and pure PFN pages. Okay, so I guess we have two kinds of pages, one that has just a PFN and one that has just a struct page. Earlier we saw that the usage of a PFN map means that there is no corresponding struct page, and similarly usage of a VM mixed map means that there may be page frames with a corresponding struct page and page frames with just a PFN. So in such cases, this function is apparently invoked. The next one is called access, and it is called by access process VM when get user pages fails. Okay, typically for use by special VMAs that switch between memory and hardware. I'm not too sure what that means either. Perhaps we will see an example and it will become clearer. The next one is called by proc PID maps. code to ask the VMA whether it has a special name. Returning a non-null will also cause this VMA to be dumped unconditionally. Oh, that's great. Okay. So what that means is when you do cat proc PID maps, you can see a certain layout, and some of the layouts have a very specific name. For example, libc.so.6 almost always has the name suggesting that it is libc.so.6. So I believe that is what this refers to. On second thought, libc.so.6 shows the path to the shared object file, if I remember correctly. So it is unclear if that and the name are the same thing, but we can do a quick search. Proc format of proc maps. We probably have an example here. Yes, so this is what I was referring to. We have the path name, but we don't have a name as such. So let's take a look. If the region was mapped from a file, this is the name of the file. This field is blank for anonymous mapped regions. There are also special regions with names like heap, stack, or VDSO. Right, so this is what the comment is referring to. As opposed to mappings that are backed by a file, for mappings that are not backed by a file, you may see names like stack, VDSO, heap, and so on. And those names can be fetched by using this name function pointer. Sounds good. We have two functions inside config NUMA, and seeing as to how our machines are mostly NUMA these days, I guess it makes sense to take a quick look. We have a function pointer called setPolicy, which adds a reference to any non-null mem policy to hold the policy upon return. Caller should pass a null to remove the policy and fall back to the surrounding context. Do not install a mpol default policy, no the task or system default mem policy. No, I'm not too sure what a mem policy is. I'm very new to it. Let's take a quick look. Mem policy describes a memory policy. A mem policy can be used associated with a process or with a VMA. For VMA related allocations, the VMA policy is preferred. Otherwise, the process policy is used. Interrupts ignore the memory policy of the current process. Right, but I'm not sure what a policy means. Does it mean the rules according to which a VMA is freed, allocated, and so on? I'm not sure. So for the time being, I'll not take a look into it. Okay, let's go back and restart from here. Yeah. So there's also another function pointer related to policy, which is getPolicy. So we have setPolicy and getPolicy, but I won't get into that either. There's another function pointer that returns a pointer to a struct page, and what it does is this function pointer is apparently called by VM normal page for special PTEs to find the page for address. I see. Okay. This is useful for the default behavior. This is useful if the default behavior would not find the correct page. Okay, this is interesting. So what it does is that given a specific virtual memory address, a VMA struct pointer and an address, it will find the correct page struct that it corresponds to. That's interesting. Yeah. Okay. Let's look at the source again. So now that we've looked at what VM operation struct is, let's continue the file. We see a function called simple remap mmap, okay, which takes in a pointer to a struct file and a VM area struct. And what it does is make a call to remap pfn range with these specific arguments. And shortly after making that call, it sets the VMA VM ops to the structure over here. And it performs a simple VMA open of VMA. Got it. So it is interesting to note that it explicitly calls simple VMA open of VMA after setting the VMA arrow VM ops to the specific value. Okay. So if you look below, you can see that this driver's function fops table will have mmap set to this function. You can see that it has a we can see that the file operation structure of this driver has the mmap set to the specific function. So what happens is that if you open this specific driver from user space and then do an mmap with the fd set to the fd obtained by opening this driver, and then subsequently then the mmap call will eventually trace down to this specific function. Now, unlike other system calls, the mmap call does quite a bit of work in the kernel before reaching the device-specific mmap call. And I have explained this in an earlier video where I talk about about tracing a binder about an mmap on a file descriptor that points to a binder driver, and we trace the path through the kernel sources from the entry point into the kernel all the way to the driver specific mmap implementation. So I highly recommend that you go and watch that before continuing with this video. So the idea is that the kernel would already create a VM area struct and pass that into this specific function simple remap mmap before as part of the mmap call from user space. And what this specific function does is that it manipulates the function, it manipulates the page tables of the current task to account for this VMA and to add page table entries for the specific VMA. That is what this particular function does, the remap pfn range. Let's take a quick look at the well, it's better to go through the sources of this function. Let's try going through the sources. Yes, so what this means is it remaps kernel memory to user space. So the VM area struct here does have a segment of memory associated with it. However, in order to be able to use it from user space, you need to remap that into user space, and that is what this function does. So VMA is the user VMA to map to. The ADDR is the target address to start at. The PFN is the physical address of kernel memory, and the size, and so on. So just to be clear, because I think I made a mistake in my description earlier, what this function does is it associates a set of user virtual addresses with kernel's physical memory by manipulating the page tables for the user process. And the physical memory argument is the third last, and that is VMA arrow VM underscore PG off. So that is going to be the page frame number of the physical memory that will be used along with this mapping. Okay, so note that this is only safe if the semaphore is held when called. Ooh, I am curious about that. So the struct does have a pointer to the mapped regions, that is the list of VMAs. So yes, it would make sense that a lock be held before that operation is performed. However, in this case, we don't really capture any lock. This might be because the calling function from kernel acquires the lock, calls the driver specific mmap, and then releases the lock. Let's go into the details. So what do we see here? We see that the end is calculated. We see that the VMA arrow is calculated. We see that remap PFN is set to PFN, and there are some edge cases that they are talking about. They say that there is a horrible special case to handle copy on write behavior that some programs depend on. We mark the original uncopy on write pages by matching them up with VMA arrow VM underscore PG off. Right. So what's happening here is that it checks if it's a copy on write mapping, and if it is, it checks if the ADDR, and the ADDR is the start address, is not equal to the VM underscore start, or end is not equal to VM underscore start, VM underscore end, then we return ein val. Okay, so this seems to be a sanity check of sorts, where you have you just check if the VMA arrow start is in fact the ADDR and so on. If it is a copy on write mapping, what eventually happens is that the VM's page off is set to PFN. Okay, so well, we did pass VM underscore PG off as PFN anyhow. So yeah, in our case, I don't think it makes much of a difference. The way it checks if it's a copy on write mapping is by checking the flags field of VM area struct, and by checking if VM shared or VM may write is set. Okay. The next function is track PFN remap, which it is called when new PFN mapping is being established by remap PFN range for physical range indicated by PFN and size, and it returns a 0. But I guess that depends on the I'm not quite sure where that is defined. For now, I will ignore that. There are also some flags that are being set. The PFN is decreased as ADDR arrow right shift page shift. There is a page directory value that is being calculated, and in a loop we are calling the functions pgd ADDR end and remap p4d range, and eventually we break out of the loop. Finally, we call untrack PFN, and we seem to be done at that point. What does untrack PFN do? Untracked PFN is called when unmapping a PFN map for a region. Untracked can be called for a specific region indicated by PFN and size, or can be called for the entire VMA, in which case PFN size are 0. I am not quite sure how this works, but it seems that it allocates, it maps a chunk of physical memory, contiguous physical memory, into the user space VMA, into the user space address pointed to by VMA underscore start. That seems to be the case. Yes, because looking at the memory management will require another set of videos, and I'm not quite sure just yet about how these various data structures relate to each other, so I will skip it for now. Okay, so the next function that we have is a simple setup cdef function. Yes, and I believe this is called from a function below, so we will go there and come back here instead of looking at this right away. We notice that look at the comment here. It says we export 2 simple devices. There's no need for us to maintain any special housekeeping info, so we just deal with the raw cdefs. So we have a array of struct cdef type and it's called simple cdefs. If you needed just one character device, it would just be a static struct cdef simple dev and not an array, and that is what you would use. If you have multiple character devices, then they would all have the same major number but different minor numbers. Okay, and then there's a init function which figures out our device major number. If a simple major number is passed from the command line, it ends up using that as the major number for the device, and if not, it will look at it will dynamically pick a major number for use using the alloc_chrdev region function. And the simple major number is set to major of dev. We can see how dev is passed by reference into the alloc_char_dev region function so that it can be dynamically picked. After that, we see that if simple major is equal to 0, then the result is what it is set to. That is, if there was no major number that was passed from command line while inserting the module, then you just pick the value that has been returned. And 2 character devices are set by you calling this function simple setup cdef. If you have just 1 character device, it doesn't really make sense to set this up as a different function, I assume. However, the arguments are a pointer to the character device, a 0 indicating that it's the 0th device probably, and a pointer to the simple remap ops function pointer. So what the function does is it takes the pointer, the minor number, and the fops, and it sets the device's owner to this module. It sets the device operations to fops, and it calls a cdev add function to add the character device into the subsystem. Okay, so the functions that we need to investigate within the character device subsystem are mkdev, cdev_init, cdev_add, register chrdev region, and alloc_chrdev region. Also, we will look at unregister chrdev region. The cleanup function is fairly simple. It just calls cdev delete on both of the character devices that have been set up, and a unregister character dev region to free the space that has been allocated for the character device. The kernel knows that these are the functions to be called upon initialization and removal, because we have these two lines here that indicate the same. Okay, so in the next video we will go through the character device subsystem in detail and try to figure out what exactly it is that these functions do. A quick note on the difference between a major number and a minor number. The major number is used by the kernel to figure out which driver is associated with a specific device, and the minor number is used by the driver to figure out which device is being referred to. So minor numbers are almost exclusively used by the driver itself internally, while major numbers are used by the kernel to figure out what driver needs to be used. Alright folks, so that's it for this video. In the next video we will look at the character device subsystem. If you enjoyed the video, hit like and subscribe.